you gain a lot more surface area.
Yes.
The surface area allows you to run more product between cleaning. So your filter, the biggest surface area is your cartridges and your bag. Your smallest area is bag only.
Yeah.
So by buying this one, you can easily have this or this,
Yes.
and less parts to clean if this works. If you need more surface area, you go to this. So that's usually my recommendation to customers. This one here, yeah, if you can actually tell me you're going to run one product in a machine forever, that's the way to go. If you're going to change products, which most customers do, they'll run 5 to 50 products in the same machine in the course of 1 year. Then this or this are the best way to go.
Okay. I also remember you put some words there saying that using bag can reduce the operation temperature. Is there or
Reduce temperature.
yeah, operating temperature using a bag.
You go backwards.
Operating temperature. Maybe here.
啊，最后
That's eliminating lowering
The stainless steel chamber walls not exposed to the product.
lowering the operating temperatures.
Well, what happens is build up a product. Okay, if you're comparing, I guess, kind of a bad slide. Yeah. If you're using a bagless machine,
Yes.
so if you're using cartridges only, when you get product on the wall, the product cools the wall of the machine. Cooling the wall of the machine cools the outlet. Most customers use the outlet temperature
Yes.
as an indication of when the process of drying is done. So if you're coating the wall with material, you're insulating it, and that can affect your results on your outlet temperature.
Okay. So it's like using bag can separate the
Right, exactly. It's not a product, the product can't reach the wall.
yeah.
So the wall is always at the same temperature. The product buildup doesn't change the wall temperature
Okay.
because there's no product buildup on the stainless steel chamber walls.
Yeah.
Excellent, we forgot about that.
Understand. Understand. Thank you.
So I think we're gonna go ahead and go on without Miss Coral. She doesn't like us anymore. You guys scare away all the girls. So we talked about the hardware for fluid bed drying. We're gonna go ahead and look at the process of fluid bed drying. The process of fluid bed drying is probably the most simplest, most boring process there is in the world. What we're going to do in fluid bed drying is bring hot, dry air into the bottom of the fluid bed, fluidize the product. There we go. Fluidize the product. As the air goes through the chamber, well, that didn't work out. Okay. As the air goes through the chamber, the warm air is going to absorb moisture. That's going to cool the air, and you're going to have cool, wet, saturated air leaving the chamber. So the red's hot coming in, blue going out. So you're always going to have the air leaving the chamber is going to be cooler than the air coming into the chamber. As you dry the product, as you go from 30% moisture to 20% to 5%, etc., as the product becomes drier, the outlet temperature is no longer saturated, and the outlet temperature is going to start going up. Most customers can correlate the outlet temperature to the point at which the product is sufficiently dry and use that for endpoint determination. Again, the air handler we talked about. Fluid bed drying, again, here's a more simple explanation. So we're taking at a particle level, dry, warm air coming in, saturated, cool air leaving the material, or leaving the fluid bed. How fast you dry, or how well you dry, is a function of psychrometrics. So again, drying is removing of water. We talked about that. The water is going to want to move from the granule, from your product, to equilibrium, to the air. So the farther the air is away from the product, as far as temperature or moisture levels, the faster you will dry. So you want to be able to bring in the drier the air, the warmer the air, the faster your product's going to give up its moisture and dry. Most drying, if you look at the application or the process, there's a constant rate, a falling rate, and an equilibrium point, which basically goes back to this wonderful little graph here. So when you first start drying, you first turn the machine on, you're going to hit this point where the surface of your product, taking the product one molecule or one particle at a time, is very wet. Because of that, the outlet temperature is falling. The moisture content is falling. The particle is giving up its moisture very quickly. You reach a point where the surface of your particle is dry. So now to get to dry it any farther, you've got to put more energy into it and pull the moisture from inside the particle out. To pull the moisture from inside the particle takes more energy, so the rate at which the temperature is changing tends to slow down. And you finally get to a point where your surface is dry and your inside is starting to dry, and it finally flattens out even more. So what's happening is your outlet temperature is falling. Your outlet temperature, not moisture. As your moisture level goes down, your outlet temperature starts to come up. As your surface becomes more dry, your moisture content is leveling off and your outlet temperature is going up even faster. And eventually, usually when you get down to like that 1, 2, 3%, you'll see your outlet temperature starts to do this number and move very quickly upward. And that's when you know you reach your drying point. So again, you want to be able to bring in dry, warm air in order to get the product dry quickly. Now I mentioned earlier, if you end up with large particles coming out of your mixer, garbage in, garbage out. A large particle, what will happen is you'll create a crust on the particle. That crust will become a hard surface. That hard surface will make it more difficult for the water inside to evaporate to the outside edges. When that happens, we call it case hardening. What happens is you open the fluid bed up and you got marbles like this. That's a bad sign. Because when you break the marble open, the outside surface is dry. You break it open and inside is moisture. So you're drying. Your percent moisture on your product when you finished was 1%. You go through the mill and now it's 2, 2.5, 3%. Because you've released all that moisture. So that's why some customers, if they don't have a good high shear granulator and good particle size coming out of the granulator, will wet mill. By wet milling, you force your particles all to be roughly the same size. That minimizes case hardening. So again, you're taking the air, you're filtering it through the air handler, you're drying it through the dehumidification grids, you're taking it past the heating coil, electric on the small machines, steam on the big machines, taking it past the inlet HEPA filter, so now you've got dry, heated, clean air. The dry, clean, heated air goes through the product bowl, lifts the product into the chamber. It comes in as warm, dry air. It leaves saturated, wet, cooler air, goes out the outlet pipe and out the fan. As you start to dry further, it's no longer saturated. As you leave the saturation point of the air leaving the machine, that's when the outlet temperature starts to rise. Because now instead of being 100% moisture, it's 90% moisture on the outlet, 80% moisture, etc. As you lower the outlet moisture, because it's harder to get the moisture out of the product, the outlet temperature is going to increase. Most customers, what they end up doing is they do what we call LOD, loss of drying. They'll take process samples, record what the outlet temperature was when they took the sample, take the sample and put it in a machine. That machine puts heat into it. It weighs it down to 1,000th of a gram of the sample, heats the sample, and records how much moisture it loses, loss on drying. That tells it what percent, that keeps taking a weight. That tells you its percent moisture. And then correlate that back to an outlet temperature to determine when to stop the process. Once they've done that the first couple of batches, they then have the number the outlet temperature they want, and they'll run to that temperature every time. How's that for, go ahead. I can see the question coming,
Yeah.
fire away.
The customer, after drying through the fluid bed, taking that product, what they doing any testing to measure the efficiency of the fluid bed? Means
What do you mean
like,
the efficiency?
You mean
They're measuring-
moisture?
Well,
any
that's
metal?
what I just said, they take the process called an LOD, so they take a sample, take the sample to an LOD device, the LOD heats up the sample, and that shows them the moisture level inside the fluid bed.
So,
They can then correlate that moisture level, because they took that sample when the outlet was 29 degrees. So at 29, my LOD is 50%. They do another one at 31 degrees or 35 degrees, my outlet temperature is 35, take a sample, my LOD is now this. And they can correlate what the LOD is relative to the outlet temperature.
okay.
And then that tells them their endpoint determination. Does that answer your question?
They measuring any the efficiency means they want to some the product. They doing any other testings on the moisture other than
Moisture? No.
Nothing.
No, because all you're trying to do at this point is take the granulation and dry it.
Okay.
They usually won't do a particle size. I'd say
Then-
most of the times they won't do particle size at this point. Particle size is a dry milling operation. Some customers will do all of it inside the fluid bed. This is another one where Pfizer's product, as easy as it is, I don't see why they do a dry mill. They theoretically could, because of what they do it all inside the fluid bed and be done. But they don't. I don't know why. If you've done your process right, you can get your final particle size coming out of the fluid bed and not ever dry mill. That would be the best way to go. Or you take your dry mill or take the product out of the fluid bed, and instead of putting it in a tote, you run it through a sieve, a screen. All your fines and all your medium products go in the tote. Your coarse products are all you mill. You don't mill everything. You just mill the big particles. Pfizer's milling everything. So the fine powders become even more fine. The medium products become fine, and the coarse become medium. I don't get it.
Okay.
So they're wasting a lot of time milling 800 kgs when in fact they probably only need to mill 50 kgs. But they mill it all. Okay, give me a second here, folks. Someone's buzzing me like crazy. I apologize here. Maybe it's Henry. So as I said, drying is the simplest process. Now drying, the act of drying is going to occur when you're doing a top spray granulation as well. The act of drying is going to be the same thing you're doing during a Worcester coating. You're putting dry, heated air into a machine. It's going to want to absorb moisture. And a drying application is directly absorbing it from your high shear granulation mix that you want to dry. In Worcester coating, your spray liquid that you're spraying onto your product is going to want to evaporate. So you've got to balance your thermal energy here. And this is a perfect time to talk about balancing thermal energies, is to actually skip up a few slides to like the second slide I showed, where I said we don't talk about this one yet. And that is the scale up on a fluid bed and how important it is and why. Wow, more than a few slides, huh? There we go. When we start looking at scalability, we start looking at drying in a fluid bed or fluid bed lift, moving a particle. There are really two major parameters we want to look at. The first one is velocity. The velocity in the chamber equals lift. Remember I used the example of an airplane. The faster that airplane goes, the easier it is to lift into the air. The heavier the airplane can be. As you lower the velocity, you lower the lift, the airplane crashes out of the sky. Same thing with a particle. Picture one simple particle was a ball. The lift on that ball, the faster the velocity is coming up, the more it's going to lift. Lower the velocity, the particle falls. Same thing in a fluid bed. So what you really want to do when you start talking about lift is control the velocity through the machine. From a scalability standpoint, what fluid air has done, whether it's a 50 liter or a 1200 liter, is basically maintain our dimensions and our fans' capabilities such that we can maintain our air velocity through the machine. So even though the machine gets bigger, the plate gets bigger, the airflow goes up proportionate to maintain the lift. The lift is what causes the particle to roll like this inside the chamber. The second major thing on any fluid bed, dry or granulation or worse for coating, is air changeovers. Air changeovers is your thermal energy. Thermal energy is your evaporative force. What's going to absorb the moisture in your air. So the air changeovers, the amount of heat, the amount of, or the dew point, the air changeovers control how fast you're going to evaporate moisture. So another thing fluid air has done from 50 to 1200 is try to maintain the volume of our machine such that the air changeovers remain constant. That one is thermodynamics 101. It's amazing how many of your local competitors, they all don't know why the machines are the shapes they are or how big they are, because they copied somebody else's. That's the reason why your machines get as big, tall, etc. But most of them don't understand it. Fluid air is maintained bowl heights, wall angles, and volume in our chamber as we go from 50 to 1200 to give us scalability from velocity and from air changeovers. That's huge when your customers start talking scalability. So keep that in mind. Thermal mass is air changeovers. Your particle moving in the chamber is air velocity. Let me jump back to where we were. How'd your meeting go, Mr. Tony?
Sorry.
So how'd your first training class go?
That's your training is better.
Oh, good answer. That's a lot of bull. That's a good answer. Well,
So
speaking of which, Thomas,
So that's why afternoon you came here.
did you book a car for this afternoon?
Okay.
Thank you. I completely forgot about it. Thank you.
So,
Because leaving late yesterday, it took me over 2 hours to get back at the hotel.
oh, 2 hours.
Yeah.
Oh, yeah.
So I'm not leaving late today.
It's a 5 or 5:30.
That's when we left yesterday,
Really
yeah.
rush hour.
Today we'll be leaving, what is it? What time's the bus come?
4:30 will be better.
Yeah, 4:30 will be better.
Yeah. So we back to your
Okay.
But do you think you can finish the training?
Well, and that's the advantage. We don't need to rush. We're not going to rush through training because we're going to do another 2 or 3 days next month.
Yeah. Yes.
I'm not sure we'll finish. We may not.
Yeah.
But we're not going to rush through anything.
Yes.
You guys need to understand this, and we're going to go through it now. We're going to review it again next month and go through the new material next month.
Definitely.
And probably in January, we'll review the material we did in December.
Yeah.
Ricky's got to know it. Diane's got to. Everybody here's got to know this material. And sales guys have gone through it a couple times. They hear my speeches and my presentations too many times a month. But the more you know it, the better you know it. When you present to a customer, the more confident you are.
Yes.
Your confidence comes off the customer. So if you're like, it's an animation video. You don't sound very confident. So when you start talking confidently, your customer will believe in you. He believes in you, he starts writing you checks. So, hardware and drying. Any questions?
So I would really wonder, just like your previous presentation about airflow and the airflow change. I think it's quite important for fluid bed.
Oh, absolutely.
So I don't know whether Arvin and Vicky are clear about that.
Actually, I don't know the meaning of
I really want to have more
the air
discussion.
changes.
Yeah.
What
Sure.
you mean?
So picture
It's so important.
that bottle. That bottle's got a fixed volume.
Mm-hmm.
Now on a fluid bed, there's air going in, there's air coming out. There's air going in and the air coming out. What we call changeovers per minute is how many times the volume of this changes per minute. So if, let's just say it was 150, I can't remember the numbers. 150 changes per minute means the volume of this chamber, of this vessel, empties and refills 150 times every minute.
哦，yeah，
That's the changeovers per minute.
换气频率。
明白了，
And the changeovers tells you, of course, how many times, how much dry heated air is coming through the machine every minute. Because remember, it comes in dry heated. It leaves saturated and cool. So if you maintain the changeovers, you've maintained the thermodynamics, the thermal efficiencies, the thermal mass
yeah，
per minute is being maintained. So now when it comes to scalability between the 300 and a 500, as long as you maintain the velocity, that's your lift, and you maintain your temperature and your dew point, because we've maintained the volume and the shape, you get the same thermal mass per minute. So you get the same drying efficiency from the 50-liter bowl, 50-liter machine to 1,200-liter machine. You're getting the same changeovers, you're getting the same drying efficiency. From a scalability standpoint, it makes life a lot easier. I'm making my batch at 100 liters right now. I decide to go to 300 liters. If I can maintain, so my velocity on my old machine was, well, it's a little different. My airflow on my old machine was 1,000 meters cubed per hour. My plate dimension, of course, as I'm the engineer, my plate dimension I know. We'll call it 1 meter for easy numbers. That means I've got 1,000 feet per second. So I got 1,000 meters per minute going through the machine. So when I scale up, my plate goes 3 times bigger. I've got my airflow meters cubed, my mass flow has to go up to 3,000 to maintain a 1,000 meters per minute velocity. If I maintain the velocity, I've maintained the lift. I have the same lift dynamics. And because the engineer did a good job of maintaining chamber shape, wall angle, volume, I now have at that same velocity and the same mass flow, I have the same thermal mass. So now my drying efficiency is now 1-to-1 scalability from machine to machine.
We will also measure the velocity of the air.
Well, what we do is we measure the mass flow. We measure the cubic feet per minute or the meters cubed per hour.
Okay.
Either one, since as an engineer I can measure the diameter of the plate. So if I measure meters, if I divide meters cubed per hour by square meters, I get meters per hour. There's my velocity.
Just think about it.
And velocity is lift. I mean, if you go back to your textbooks, the lift on an airplane or lift on a particle is 1/2 the density, the velocity squared, the surface area, the coefficient of lift, the square root of that. But density drops out because you're comparing apples to, you're comparing same temperature to same temperature. So the density of the air becomes the same, cancels out. The particle size, we're comparing one particle to the same particle, so surface area drops out. Coefficient of lift drops out for the same reason. So you're left with the square root of velocity squared, which is velocity. So velocity becomes your lift. If you can maintain the velocity when you go from machine 1 to machine 2, you can maintain the lift on your particle.
Yeah.
And you can do this on any fluid bed, whether it's mine or somebody else's. If you know the cubic feet per minute, and you can measure the bed plate, you know the velocity. Which allows me to, which is what we do now when we do our scalability training. For my machines, it's easy. I'm the engineer. I know my diameters.
Yes.
But if you're talking a glot or an aromatic or a GEA, we tell the customer, go measure the bed plate.
Yes.
Give me the dimensions of your bed plate. Send me your data log. The data log shows his feet per minute. Sorry, usually his cubic feet per minute. His data log, or the bed plate, gives me my area. With those two, I have velocity. I can now scale the lift from every machine in the world with those two numbers. Now, air changeovers is a thermal energy issue. I don't know if a Glot or GEA, how their numbers compare. We'll just say we don't, I do. Now, again, it's a simple measurement. We measure 3 or 4 places to get the dimensions of their chamber. Once you got the dimension of the chamber, you already know the mass flow, cubic feet per minute. Divide that by your volume and you get changes per minute. Now you can compare thermal efficiencies. So if the machine you're going, if you're scaling from fluid air to fluid air, we've maintained that ratio. But let's say you're going from a domestic machine to mine. You take the measurements off the domestic machine, find out that crap, we have a higher changeover rate, which means we're going to have a higher drying efficiency. That's a good thing. If it's lower, you can now adjust your temperatures to maintain the same drying efficiencies. So really, with a few measurements and cubic feet per minute on the machine, you can calculate everything needed for drying. If you got inlet temperature and inlet dew point, your air volume, or your machine's volume, your machine's cubic feet per minute, you've got velocity, you've got changes, you've got thermal energies, you can then balance them from one machine to another to maintain scalability. How's that for a lot of chew on, huh? That's a lot in one sentence, I know.
So Evan, you didn't get that kind of information in your previous right? No. No,
Yeah.
because I rather work for Bosch and just
Right.
just check whether you get such kind of information or not.
No, not such kind of information.
And that's why we're taking our time. I noticed a lot of material. That's why we're taking our time today.
Yeah.
It's why we're not rushing through this. It's why we're going to review it
Yeah.
the first half of next month. Next month's training, the first half day will be review.
Yeah.
Because now you've written it down and you think about it, you can give some thought and figure out what the next questions are. I don't believe in rushing training. I don't believe in a formal lecture sitting up here and just reading off my notes. It's an exchange of ideas and information. Now normally I throw candy at people to keep them awake, so when Thomas falls asleep I hit him in the head with candy.
Thomas is calculating.
I can see right now, look at him.
He's drawing like calculating.
Oh, I thought maybe he was doing a drawing for his son. His son's the artist. Your son's the artist.
But sir, I have one question. So
Yeah.
can say we are the only manufacturer, we are the only fluid bed who can, when scaling up, we can maintain the same velocity and the same changeover. Can we say that?
No.
No.
Well,
And if
I've never calculated the entire product line for a competition.
okay,
Obviously, I've done the dimensional analysis on my equipment.
okay,
Um,
but we are.
I would imagine I'll say any of your foreign competitions should have this
Should have this.
and should know it and should be able to tell a customer about it.
But our
Your
boat,
local guys, I don't believe,
yeah.
because they have no idea what they copied or why they did it.
But our bow are same height and the same angle. But glass bow is not like that.
Well,
Huh?
the Glot drying bowls,
Mhm.
when you go from drying 1 to drying 2 to drying 3, I don't know.
Okay.
When you start switching from a drying bowl to a granulating bowl to a coating bowl, everything has changed.
Yeah.
But I don't know about a 50-liter dryer Glot to a 100-liter Glot dryer to a 500-liter Glot dryer. I've never done the calculations across the entire product line
Okay.
to see if they've maintained the scalability numbers. I'd have to assume they had from dryer to dryer, but that's where your competition really makes things hard. Let's just say they did. So they're dryer to dryer to dryer, the changeovers are good. But now you change the bowl out for top spray granulation, or you change the chamber. You just made it that much more difficult on your competition, on your customer for scalability. We don't change the chamber for that reason. The idea is to make your life, the customer's life a little easier, not a little harder.
角度可以一样从小到大，高度就不可以。
锅只说的是锅，
只说锅
Only bowl, not chamber. Only the product bowl.
这个，
对。
然 后保证它同样的线速度，风的线速度。
事实上，让来讲，
但是能计算吗？通过那个风量，就是他说的 cubic feet per minute 是吧？
这可以计算。
可以计算。
所以是吧
I'm listening. I'm listening. I'm sorry. Go ahead.
没有，你气速的计算就是用你的气量，你风量值不是有吗？
对，
对吧？用的风量除以你的那个截面积，这个气体风盘的截面积不就是速度吗？体积除以面积不就是速度吗？
对，
这是你的 air velocity， 对不对？它是你放大的时候，你首先要保持 air velocity 相同，因为 air velocity 决定的是这个空气给了你的物料多大的提升力 lift， 它实际上反映的是你的硫化状态。国内厂商在谈这个时候，他会讲你怎么做的，你观察它的硫化状态一样不一样？但实际上你要首先要计算要有数值，知道吧？然后其次他讲的是你要保证这个，因为这个 air velocity 是决定它的硫化状态，什么叫硫化高度，对不对？然后是它这个 air change 实际上是换气频率，换气频率实际上讲的是它的这个热交换的这个能量传递了多少。
对，
这个可以理解吧？
哎，我刚刚其实看他那个图，这个可以理解。
对。
他看他那个图，他那个小锅最小那个，哎，Ron, can you change the presentation to the scale ability?
Yep.
我看它小的话也到达100多的换气率，140多，150多。
没，它那个数据只是一个数据，它只是举个例子。数据那个数据只是一个这个数字，知道吧？它并不是说你换气的时候一定要达到这个换气率，不是的。肯定不是啊，因为你的气量大、气量小的时候，换气率是不一样的呀。
就这个。对啊，你看我看它50的话。
So this number is just a number. This number is just.
Right. There's nothing that says this number that 165 changeovers is better or worse than, let's just say the other competitor uses 185. There's nothing that says that 185 is better than 165. What you're trying to show is scalability, that you've made it. Because of your design, you've maintained wall angle, volume, velocity. You've made it simpler for your customer to scale from R&D to pilot to production. Because there's big costs here. So he wants to go from the pilot machine at 100 to a 500 liter like that. The fast, without doing 3 months of PQ like our friends in Pfizer are doing. They want to do it immediately. So how do you make your life easier? Well, one of the ways is to maintain velocity.
Yeah.
One of the ways is to maintain the changeovers. So now you've eliminated the thermal mass issues from their process, and you've eliminated the lift, the velocity on their particles. So now you made it very easy for them to know exactly what airflow to run at in order to maintain thermal energy and lift. You know it immediately.
这张表里实际上显示的是，你看从50到100到最大的，当我的这个速度是比方说300左右的时候，我的 air change rate 你看都是这样，明白了吧？
对，为什么呀？
它如果变大了，
自己去算。
因为我注意到它这两个数据是，你看.4结尾的前面都是7，它是什么？
它肯定是对呀。对呀，这个 air change over 和一个 airflow 应该怎么换算？你自己算。
不是换算的问题。
airflow 乘以时间不是？
比如 airflow 是指的气流的速度，
对。
但是这个是换气的次数。比如说我一个小锅跟一个大锅，我气流的速度在里面是一样的话，
那我速度不一样。
气流速度。当我气流速度一样的，
气流速度一样，
换气速度一样的。
怎么讲？如果说我大的锅，我可能需要1分钟才换才，比如说我说1分钟换20次，因为我小的锅我同样的速度是快嘛，1分钟换的次数 ，air change 的次数。
想想。
So what's the question?
Just think about.
Oh, it's a tough to think about, and that's why I said we're not rushing it.
Yeah.
There is a lot, especially for you two.
Yeah, we are.
The rest of you are going to ask. The rest of you are going to ask
因
me.
为它这里面有方程，有换算的方程，它没有直接给你说出来，对不对？你换算一下，这是它给你展示的一个结果，就是当我们在小锅里边，这是有一个前提，是吧？这有一个一定的风量。那么小锅的时候，当到这个换气速度的风量和大锅的时候，这个换气风量是不一样的嘛？
对，风量是不一样的啊。
气速一样，风量不一样，对不对？因为截面积不一样嘛。
反正我一直在想，那个角度会不会影响它的换气速度？
它就是角度，然后截面，说白了它唯一那个变成就是那个截面。体积，像你这个体积，
如果那角度变了，不是76度，会不会也会维持这样的一个数据？
对了，差不多，我想明白了。
应该不会。
想明白没？为什么这个没有？
76度。
你要记得那个什么？它这个，它这个，比如说这是个小锅，这是个大锅嘛，对吧？你同样的速度进来的，这个比如说30升每分钟，咱不用刻那个set是吧？每分钟，这个是3000，
你想要把上面那个下面连一下，
可能平均。
哦，是的，明白。所以你处理这个的话，速度是一样的，但是你流量大。
API.
所以换气速度，比如说我那个这个是60那个1分钟换2次，这个是6000。
think about the wall angle, why it is 76 degrees,
对吧？
Why is it 76 degrees and not 45 degrees?
Yeah, one 45 and one 50 or.
Yes.
It's clear for me.
Is it clear?
Yeah.
So they are clear.
I'm clear.
The main
Then you can explain to
the main reason
guys.
the main reason it's 76 degrees really turned out to the ratio of how fast we wanted the particle to slow down. If you make the wall like this, so I'll go from 90 degrees, the diameter stays the same. The velocity doesn't change, and you got yourself a Glock machine. The older Glocks was a cylindrical chamber. At 45 degrees, the chamber becomes so wide that the particle slows down too fast. So it lifts out of the bowl and goes bloop, bloop, because your diameter is changing too quick.
Okay.
So we basically experimented with different wall angles until we saw roughly I want the particle to go into the chamber, go up, not too high, not hit the filters and break, come back down and repeat. So we looked at different angles and kind of came up with 76 being what we liked as far as particle movement, as far as particle slowing down in the chamber based on the change in diameter. So would 74 have been better? I don't know. We know 45 wasn't good, 60 wasn't good, 90 was terrible. So we kept experimenting until we saw the Reynolds number, the particle slowing down based on change in diameter at something we thought was sufficient. And then once we chose that angle, we said, that's it. Same angle on every machine. So we can scale up.
Oh, I have the last question.
Yeah, no, keep going. You're fine. You're fine. Don't worry about it.
You know, for the lab machine, we may only need to lift maybe, for example, 5 kilometers, 5 kilogram
Sure.
product. But for the production machine, we may need to lift 500 kilogram product. So what's the exact velocity we need to refer to?
If you look at the chart here, it says 50 to 1200. When you start playing around with Model 5s and Model 2s, they are very difficult to scale, simply because they're so small, and customers want to run such a little itty bitty batch. So let's assume a Model 100 to a 300.
100, okay.
Okay?
Okay.
I'm sorry, yeah, Model 100 to 300, make it easy. You're running the 100, for scalability, we kind of got off track, sorry about that. We're talking scalability. So if you're running a Model 100 and you're running a bed depth, the bed depth is half the bowl height.
Okay.
When you go to a 300, if you keep the bed depth the same, okay, half the bowl height, because the bowl got bigger, so if you added more material, but you keep the bowl height the same as far as material loading, your scalability is very easy, because you're still going to use this equations here to maintain your velocity. Velocity is lift. So I take my meters cubed, I multiply what I was doing at the 100 based on the area on the 300, that gets me my velocity, that gets me my flow rate. Done. Now if your bed height changes and you go from 50% on the 100 to 100% on the 300, you've gone up by a factor of 2. Now you've got to add more air on the 300 based on the bed depth of material. That's where your bed depth comes in. That's right, and that's why I would tell a customer before he goes to scale up, take his 100. If you know you're going to run the 300 maxed out, run the 100 maxed out.
Okay.
And then the scale is easy, and you do it at cheaper costs. If not, you got to rely on math to get the 300 numbers.
Yeah. But as I know, some customer like from lab to the production.
Right.
No pilot.
Right, and you can do it. There's more testing required because you're adding so many different parameters. But going from, say, a Model 10 to a Model 300, that's not too bad. The problem is when customers try going from like a Model 2, running the smallest batch, to a Model 500, running the biggest batch. Not only have you gone machine-wise 25 times, right? Yeah, no, 250 times.
Oh yeah.
You've also gone from a bed depth of the smallest to a bed depth of the largest. So you probably put 500 times the scalability up there. That's where you get in trouble. That requires a lot more testing work.
Okay.
Let's go ahead and move on to granulation. Excuse me. Oh, I go too far? No. So everything we've talked about in fluid bed drying, the chamber, the plenum, the bowl, the filter bags, the chamber shape, the effect of lift based on diameter changes and velocity slowing down, thermal mass, air changeovers, everything we've talked about previously is going to apply now to top spray granulation. In top spray granulation, what we're going to do is place a spray nozzle into the chamber going in through the window. We're going to spray down on our product. The your product will go through the spray. The product becomes wet. Goes up in the chamber, collides with other wet product, sticks together. Basically gluing pieces together to form a granulation. Now, okay, so what do we add? Now we're going to add a spray system. We're going to add a spray nozzle. We're going to add some kind of dual fluid spray nozzle. So we're going to use some kind of compressed air to create a droplet. We really haven't added much more. So in a fluid bed dryer granulation, there's a definition here, also known as agglomeration, involves suspending particles in an airstream. What's a fluid bed? Suspending particles. Look at that. Spraying a liquid from the top down onto the fluidized bed. The particles in the path of the spray get slightly wetted, become tacky, collide, and adhere themselves or glue themselves together. During this whole process, though, drying is occurring. You can't keep the particles wet, so they collide in the chamber, they slow down, the hot air is hitting them, is drying them and gluing them together. Remember, think of two things that are wet. You glue them together to come apart very quickly. So you need the air changeovers to create the heat to dry the particles to get the glue tacky to stick. So here's a real simple graphical representation. So you've got your liquid with binder. You've got your powders already in the fluid bed. So you put your fine dry powder in the fluid bed. So remember, drying, we put wet particles in the fluid bed and dry them. Top spray granulation, you're going to start with dry material. Very fine dry material. We're going to put the spray nozzle in and spray down on them. The particles are going to become wet. We're going to create a bridge, and we're going to form a granule, an agglomerate structure by gluing pieces together. It's actually a neat process. When you start running a top spray granulation, the chamber window, or the chamber back here in the Model 2, immediately becomes hard to see through. The fine powder sticks everywhere. But as you start to form the granule becomes coarse, like sandpaper. That sandpaper starts to clean the windows. And all of a sudden your chamber window will go clean, because you formed a granulation, an agglomerate structure. So why do we form this? What's the use of forming a granulation? Same thing it was in the mixer. Better flowability, better dust control, better compressibility when you go to tablet pressing. Most of these powders get pressed into tablets or pills. So the same reasons you were doing a high shear granulation are the same reasons you would do a top spray. But there are some significant differences. The high shear granulation normally is a more dense, harder granulation. That granule will be harder to break apart only because the mixer puts a lot of energy into it. More energy, tougher bonds. Top spray granulation creates a weaker bond. That can be good or bad depending on what the downstream process is, what the customer's needs are. Which is why in top spray granulation is very careful, because you can create the granulation, and if you don't create a strong granulation, when you dry it, you create it all back to dust again. So it's a difficult trade-off, how you do it, when you do it. If you can do it in a top spray, one machine to clean, no wet milling, two less machines to clean,
Yeah.
you've made your life easier. If you can do it in a top spray. When you start talking like Pfizer doing 1,000 kgs at a time, I've done 800 kgs at a time. That's a lot of work. I'm not sure I'd want to do their 1,000. Especially their process, because their binding agent is water. Very weak bond. So it breaks very easy. So you need to get as strong as you can using a high shear mix. The hardware that goes into the machine. Now remember, drying, we still using the agitator, we're still using the air handler, still using the fan, temperature control, dew point control, the bowl, all of that has stayed the same. The chamber, unlike our friends at Glot who switch out the chamber, we're going to use the same chamber and the same bowl. So all of our geometry stayed the same. What we're going to do is we're going to add a spray nozzle inside the machine. Depending on the size of the machine, we're going to add multiple nozzles. So here's a model 120, single nozzle coming in through the chamber window to spray down on our product. 1, 2, 3, 4, 5. So here's a model 500, 5 spray nozzles spraying down onto our product. Couple things to note in this picture. Fluid Air is the only one that provides an automated system for raising and lowering the spray nozzle. Why would you raise and lower the spray nozzle? When you first put your powder in the machine, it's very fine, very small. It fills every crevice. So the bed is this tall. As you create the granule, because there's more void space, the bed's going to grow. As the bed grows, you want to raise the spray nozzle. Your competition requires the customer to stop spraying, dry the particles so it's no longer wet, stop the fluid bed, take the nozzle out, reinsert the nozzle at a new height, reheat the fluid bed, then start spraying again. Doesn't sound like too much, 10, maybe 15 minutes. You add 10 to 15 minutes per batch in a production environment running 12 hours a day, you probably added, say instead of 45 minutes, 1 hour. I just did, if I can save you 15 minutes per batch, I can make one more bowl of material per 12-hour shift. One more bowl of material is how much money in your customer's pocket. That's how we sell it. We're not the cheapest. I'm going to give you one more bowl per shift. What's that worth to you? Most customers will tell you that their bowls are worth, I've heard everything from $20,000 to $1 million. Okay, take $20,000. You made them $20,000 more a day. My spray granulation system costing $100,000 more than competitors, pretty damn cheap. 1 week return on investment. So keep that in mind. Other unique thing about us, we do not use cluster nozzles. Who knows what a cluster nozzle is? Come on, this is spray systems. You know what a cluster nozzle is.
Cluster now? No.
You don't. I'll cut you a little slack. So picture an assembly that has 6 spray nozzles in it. So liquid comes in and comes out all 6 nozzles at the same time. One liquid input to that spray nozzle. One air input to that spray nozzle. So all those nozzles get driven from one pump head. Okay, I can see advantage behind that. One pump head, one motor, 6 nozzles. That's perfect. Lower the cost of manufacturing for me. The problem with this is 6 nozzles being driven by one pump. If you plug one nozzle, what happens to the droplet size of the other 5? Pump is still turning the same speed, right? You've now taken away one nozzle. What happened to your droplet? Come on, spray systems.
Become bigger.
What, the droplet becomes bigger.
Yeah.
Exactly. So you just changed your process. You just added variability. Your droplet became bigger. Your particle now gets wet. Too wet.
Yeah. Your
particle is no longer agglomerating. It's dissolving because your droplet got too big for it. So what fluid air does is our system, we use one pump head per nozzle. Every nozzle has its own pump head. One nozzle clogs, I can turn off that nozzle and not affect the droplets the other nozzle. All the pumps are driven by one motor. So back here is a motor, one shaft. In this case, it's 7 pump heads. All 7 are running the same speed. Peristaltic pumps, remember your mixers, give me so many grams per RPM. So based on RPM, I have the same liquid going to each pump, or coming from each pump, going to the spray nozzle. I plug one nozzle, I haven't affected the other ones. The other 6 are still using the exact same liquid rates. Your total process time might change, but you're not changing your droplet size. What we do is we actually use a pressure transducer for every spray nozzle. So in this case, I would have 5 pump heads, 5 individual liquid lines. Back at the pumping station, I would have 5 pressure transducers, and if one of those pressure transducers saw a high pressure, because a nozzle was plugging, bearding, plugging, for whatever reason, dissolved solids plugging the nozzle, I would automatically turn off that nozzle by closing this pinch valve. This pinch valve's on the suction side. So I can close it, the pump can keep turning, and I won't create pressure to the pump or to the spray nozzle anymore. I am now running with 4 nozzles instead of 5, but I've not impacted my particle size or my droplet size. I have not changed my process. Huge. Even bigger when we go to coating. But in granulation, this is the difference between a bed stalling. Start overwetting a bed because your droplet becomes bigger, and instead of being a fluidized bed, it gets too wet. Product becomes heavy. The product no longer lifts, and you end up all your products sitting in the filter plate, being sprayed by more liquid, and you make a soup bowl inside the fluid bed. Ask me how you know I've done that more than once.
Wow.
Now the downside of this is very simple. Instead of having one pump head, I now have 6, or in our story here, 6 pump heads. One motor, 6 pump heads. I've now got 6 pinch valves. I now have 6 pressure transducers. So I've added a lot of hardware. Of course, the software to handle it all. Again, one batch material. Change your droplet size and try proving to the FDA or the CFDA that you have not changed your product's quality. What product was it last year that the CFDA found 21 generics that were not equivalent?
Not 21, not equivalent.
Not equivalent. Remember that?
No one is equivalent.
There you go. So this is huge. If you're not maintaining your droplet, you'll never maintain equivalency. So, very important. Now for fluid air, obviously, let me go back. Your liquid pump, in this case, so we've got a tank over here going through a strainer to a manifold and back to our tank. We pull off a manifold with each individual line through a pinch valve, through the pump head to a pressure transducer. The reason we recirculate the water through the manifold, we keep the velocity up, you don't have solids dropping out of suspension, is the only reason. The other nice thing about peristaltic pumps, if you start seeing the pulsing effect, in fact, Tony and I helped a customer of his with someone else's machine because they were complaining about the pulsing and didn't understand how to fix that. Peristaltic pumps are easy. Go to a smaller tubing, increase the RPM, you get the same flow rate. But now your lobes are spinning faster and you don't get the pulsing effect.
Did it for Hungary?
Yep, that's what it was, yes. Yep, yep. Did they buy a machine yet?
I bought a pilot flew back, left flew back.
Okay, good. You did a lot of work to help
We
them.
should have sold another pilot pressure meter, but
Yeah,
just
yeah.
a little bit.
Don't get me started. So here's a simple, what I showed you in a picture. Here's the graphical form of it. So you've got a tank, recirculation pump, taking liquid from the tank through the manifold back to the tank. You've got 3 pinch valves off feeding 3 pump heads. Those 3 pump heads feed 3 pressure transducers. Those 3 pressure transducers feed 3 nozzles. That's your entire liquid delivery system. More expensive than a cluster nozzle. Cluster nozzle would have 1 pump, 1 motor, 1 pressure transducer. But again, you would affect your droplet size. Anytime something happened to a spray nozzle, you would affect your droplet size and never know it. All of our top spray granulation nozzles are dual fluid nozzles. A dual fluid nozzle, all that means is there's 2 fluids. One is your liquid, the other one is air, atomizing air or atomizing nitrogen. That atomizing gas, what we call it, is what creates the droplet size. Increase the pressure at a fixed flow rate gives you a droplet. Increase the air pressure, the droplet becomes smaller. Pretty straightforward stuff. Again, spray system spray nozzles. So we control the liquid pump speed, which controls our flow rate. We automate the atomizing air pressure, which controls our droplet at a flow rate. Of course, since we are using, oops, did I miss something? Wow, wow. Bad presentation, Mr. Siag. Fluid air has 3 types of nozzles. We use a standard non-self-clearing nozzle. We have a self-clearing nozzle and an in-process removable nozzle. For top spray granulation, we don't have in-process removable. All of our nozzles out of their spray systems. Here's a selling point. Who makes the best damn spray nozzles in the world?
We are the best, of course.
Exactly. Your competitors do not make their own nozzles. Your competitors go to a book, choose a nozzle, and put it in their machine. Our nozzles were designed for our machines by spray systems, which means we've got our pattern set via the Doppler radar, what's going on in our fluid bed, by spray systems. Everybody else is just choosing something that works. Ours has been optimized for our designs. And again, who makes the best nozzles is right here in this room. Your competitors don't make their own nozzles. In fact, some of your competitors have no idea what nozzle to use. Tony and I joke about it every time we go to the local trade, the big trade shows, because all the local guys, you ask them what nozzle you use, they will respond, "What nozzle do you want to use? What manufacturer do you want to use? You want to use a Leckler? Okay." They don't care what nozzle you use. So, you win hands down. A couple things to keep in mind that affect granulation. The agitator. Normally we won't use the agitator because it'll actually put energy into the product and break it. If we do use the agitator, it'll only be after a bag shake. So you've got wet material, you've done a bag shake, and bag shaking and granulation is where it really comes in handy. You start out with a very fine powder. That powder is now stuck in a filter bag. You process for the first 20 minutes. Big machine can have 10 kilos, 5 kilos in the filter bag. You process for 10 minutes, you stop the airflow, you shake the filter bag, all that 5 kilos comes back down to the bowl, where it can be wet, where it can become finished goods again. Lot shakes the 2 filter bags. The 5 kilos goes from this bag to this bag, back to this bag, and repeats. It never goes back to the bowl. This is where we improve our yields over our competitor. And again, what's 5 or 10 kilos out of a couple of hundred? Not much. 10 kilos a batch, 5 batches a day, 25 batches a week. There's 1 bowl of material you made the customer per week. What's that worth to them compared to the cost of the machine? Now, I make it sound easy. Tony and Thomas can tell you, trying to convince the customer that it's worth the extra $100,000, never easy. But this is what our job is. We've got the better equipment. We've got the better design, the higher yields. It's convincing the customer that money up front is worth the savings every week. That's a tough one. Most procurement people, all they care about is the dollars today. The operations people care about dollars next week. So it's 2 different groups we have to win over. This one is huge, the way we shake the bag. Droplet size, obviously, at a given flow rate, the only thing that's going to affect your droplet is the atomizing air pressure. That's why we use a dual fluid nozzle. Liquid delivery rate. As you increase the liquid delivery, you increase the droplet size. So if you got a product that's not becoming big enough, fast enough, you can turn down the atomizing air pressure, or you can increase the flow rate. Here's the other advantage spraying systems has. Most of your competitors, including Schlick, won't give out or won't talk to anyone about droplet size of their nozzle. They guard it like it's the Holy Grail. You know your droplet size. You have the curves. You made the spray nozzle. See, Glott doesn't make their nozzle, so you have to call Schlick and convince Schlick to give them information to give to a customer. Schlick doesn't like that because they don't know if your customer's going to make their own nozzles, so Schlick won't talk to them the way you do. You have the knowledge right here in this building to say, okay, you're using a nozzle, whatever. Based on that nozzle, based on your flow rate, based on your spray air pressure, here's your droplet size. What size is your powder? Okay, you want to go bigger? Here's some options. You have the knowledge on your nozzles. You own it. We have to capitalize on that. Things to consider: inlet temperature, air changeovers. If your air changeovers increase or your temperature increases, you run the risk of spray drying in a fluid bed. So your spray liquid coming out of the nozzle is drying before it can actually become tacky on the particles. So you gotta be careful not to over dry or overheat the material. Your binders will have a significant determination on final particle size. A strong binder will create a much larger, more quickly growing granule, and a stronger granule that's less likely to break up in a fluid bed. Remember, in a fluid bed, you make the granule up here. It goes back through the powder, you make another granule, and you keep repeating. But when this granule collides with the side of the chamber, or the top of it, it's over fluidized, it hits the top of the chamber, the bottom of the cartridges. It hits it, you break it. So now you just formed the granule and you broke it again. So it's a repeating process. So you gotta be careful not to over fluidize a top spray granulation. And since you start with fine powders, top spray granulation, you start out with low airflow. As the powder becomes bigger, you increase the airflow. That's the opposite of drying. In drying, you start out wet. So your airflow starts out high, and you lower the airflow as the particle dries and becomes lighter. You've got to be able to do that in a controlled manner, or you end up over fluidizing one or the other. Hot spray granulation, like I said earlier, is a neat process. When you first turn it on, the chamber window goes blind immediately. Can't see anything. As you form the granule, it becomes like a sandpaper, and it starts to clean the machine for you. It's kind of cool to watch. I enjoy it. Nozzle position. We are the only one automating the nozzle position. And the customers would tell you a big deal. It's 5 or 10 minutes per batch to adjust it. Bears a batch a day I make that they don't. They'll tell you they don't adjust it. Okay. If you don't adjust it, how much spray solution ends up on the bowl? If the nozzle's too high to start, you spray the bowl. You've wasted spray material on the bowl. How much does your spray material cost, Mr. Customer? $10 a kilo? $1,000 a kilo? If you just sprayed the bowl, you've wasted all that material. It's made you nothing. What did it cost you? And I got some great pictures of people spraying the bowl. I have a picture of Allergan Forest, one of the largest companies in the world, sprays their bowl. They don't want to raise the bowl or raise the nozzle because they couldn't duplicate that on their Glock machine. So they overwet. The entire bowl is red at the end of every process because they can't change position of the nozzle. We do it automatically. It's on a pneumatic cylinder. Remember the picture, it's on a pneumatic cylinder, and we can raise and lower it on command. As we all love graphics and videos, here's one. You can see all the smaller particles flying around, colliding with other particles, forming an agglomeration. That is the end goal. The problem is as you glue it together, you can be knocking it apart as well. So there's a fine balance. Don't over fluidize it. Don't over dry it. Don't make it overly wet. And that's where your process validation people earn their keep, is making the adjustments to get all this right on the process. The fundamentals we've kind of touched base on a little bit. Bag shake. The bag shake is really an exciting thing. Too many bag shakes and you end up forming huge clusters because you dropped the bed and it's wet. Too few bag shakes and all your powder stays in the bag and you end up with lower yields. Lower yields cost us money. We don't want to cost us money. The airflow we talked about. Too high of an airflow, the particles will hit the top of the chamber or bottom of the filter cartridges and break. Too low of an airflow and the fluid bed can stall. Basically not fluidized, you're getting it wet. You start out with a low airflow. You start spraying on it, you don't have enough airflow, the bed becomes wet, becomes heavy, doesn't move, and you create soup inside the fluid bed bowl. Remember I told you earlier, chamber shape for drying, okay, it's nice, it helps us. Chamber shape and granulation is exactly what we wanted. The particle goes through the wet stream, the chamber is tapered, the velocity slows down, the particle falls back through the wet stream and repeats. Better yet, the particle's not going, because it's not a cylinder. A cylindrical chamber, the particle has to go very high in the chamber. Slow down and fall. Gravity, the farther you drop something, the greater its chance, the greater energy, gravitational potential energy, the greater chance that particle is going to break. So by keeping it low in the chamber, you prevent the breakage, you create a more efficient process. Clustering we've talked about, fines and nozzle position we've talked about. So here's kind of an idea of what we're talking about. Your competitor's nozzle, is this a better picture? Yeah, it's probably a better picture I have over here in this slideshow. So our nozzle's on a cylinder, we can raise and lower it. The competitor's nozzle comes in fixed through the sidewall. And when they want to raise it, they stop everything, they pull the nozzle out, they raise it up. That's how they raise and lower it. Cheap. Don't get me wrong, it saves, for counting fabrication, it probably saves $10,000 to $15,000. But again, if I make one more batch per 12-hour shift, you don't think I've made you back $12,000 in one day? Times how many days you run that per year? You're making the customer money by not taking it apart. Furthermore, you don't have an operator taking apart a running process. Most of your process errors happen because of us, operators. Someone forgets to tighten a bolt. They open up the nozzle and they drop something into the machine. They pull the nozzle out and they slam the nozzle into the side of the machine and damage it. They usually don't care. They're only making what, $2 a day? They don't care. They damage it, put it back in, keep running. Don't care. We eliminate the operator because our nozzles are automated and moving up and down. We're not relying on an operator to take care of it. The other neat thing about our being spray systems is because we use a chandelier for our spray nozzles, not one nozzle sitting in a cluster, we position the nozzles just like in a mixer. Remember I told you in a mixer, the mixer's nozzle is positioned to put the majority of the liquid where the majority of the powder is. To put just enough liquid where you have a little bit of powder. Same thing in a fluid bed. Through the computational flow lab at Wheaton, we know in a standard operation where the majority of our powder is inside the fluid bed. Well, what we have is overlapping cones of spray. So the wettest part of the spray pattern is in the area where we have the majority of our powder. The outside edges have some powder, and that's where we have some of our liquid. We've optimized the spray pattern based on the computational flow lab to ensure optimal performance. Your competition who's going out and using everybody else's nozzles, doesn't care whose it is, they haven't done any of this work. So if you save the customer 5 kilos of spray solution per batch, what's that save them? Save them a couple of minutes per batch. What does that save them? Return on investment. Questions on granulation, drying hardware, granulation hardware. Remember, there's a test later. What we're going to do before we get into coating is take a break. Coating is going over a lot of hardware.
Okay.
We had a lot of hardware for Worcester coating. So rather than slam through that, let's go ahead and take what do we got here? 38, 10 minutes till. Let's meet back at 10 minutes till, and we'll go start over the coating process. Coating's going to be exciting for you. You're used to your Hootling nozzles, so you're used to one nozzle in a fluid bed, right?
Yeah.
We're going to start off with one nozzle, and then brace yourself. We go as high as 9 nozzles in a fluid bed.
9 nozzles.
9 nozzles in our production units. Building when we started. So who here has ever done coating or knows what coating is? You've done coating.
Yeah.
Obviously Arvin has. Diet, Ricky?
No.
Nope. Okay. Well, coating is basically taking a single individual particle and film coating it, putting a coating through that one particle. You're not trying to grow the particle per se as much as coating it. So what we're going to do in a fluid bed, we're going to have a very simple animation here, is we're going to take an individual particle, sprayed with small controlled droplets, getting it wet, forming a final coating. Now under an electronic microscope there on the right, you can see the core. This customer actually put 2 coatings on it. So you can see the 2 thin layers of coating there on the electron microscope. That's what we're trying to do. Now, we can do this. We can coat granules. Particles. We can coat spheres, granules, or tablets. When Worcester coating first started back in the 50s, they were really taking a sugar sphere. The sugar sphere was nothing more than that. And they would spray active onto the sugar sphere. Well, it's metamorphed and grown up to the point now where they're taking the active as a sugar sphere. So instead of being sugar, it's an active. They're then spraying a coating on it to get dissolution, to get dissolution, to get dissolution profiles, absorption rates into the body. And then you get real crazy, you can put multiple layers on it to get some to release fast, some to release slow inside the same capsule. Then it metamorphed to granules. So instead of coating a 60 or 40 mesh sugar sphere, they're taking individual granules and coating them in a fluid bed. and then taking those individual granules and putting them in a tablet press. Of course, we can do tablets. We'll talk a little bit about tablets in a fluid bed here shortly. The big one here in the last 5 years that we see, and we see a lot of it, is mini tabs, very small tablets. So let's picture a tablet that's 0.8 millimeters in diameter. 0.8 to 1.2, 1.3 millimeters is a mini tab. So they coat that mini tab, and they put that mini tab into a capsule. And based on the number of mini tabs in a capsule, or the colors of the mini tabs, the coating, they get different dissolution profiles in one capsule. That's become huge. The baby boomers, as we call them in the US, don't want to take 10 pills a day. They want one. And they want one that gives them the first kick of medicine in the morning that they need. Yeah. So they hit a big rush of medicine, and then a nice continuous dissolution all day long is what we want. They're doing designer drugs using, I call them designer drugs, designer products, where you get dissolution profiles, especially for antibiotics. Antibiotics, you want to hit, then nothing, then a hit, then a hit, every 4 hours.
Yeah.
So they're doing crazy things like that. We see cold medicines where they're doing sustained release with a hit, sustained release, and then another hit. So they're doing that all with coating applications. Heart medicine is the same way. So this has really metamorphed into a very large market. It used to be, I say small. Now every machine we look at, someone's coating something with it. And they want to coat something different. They want to break into a new market or new industry. This is it. This is where big money's at. Drying products, net margin. Granulation products, and then you've got these coating products. Coated products usually have the largest margins of any products. That's where customers make their money. That's where your customers want to make products. So, how do we coat a product? We're going to start with a very simple analogy here. That ball bouncing around could be a sugar sphere, a granule, a tablet, a mini tab. It could be anything. Is what we're trying to coat. So we're going to take the product underneath the coating column. Excuse me. As it goes under the coating column, we're going to spray it with a very fine controlled droplet. It's going to go up into the chamber where it's going to dry. It's going to fall back down outside the coating column, work its way back under the coating column, and repeat thousands of times. I've had coating applications go 4 hours for a batch. I've had some go 22 hours. 22 hours is usually patent breaking. Nobody really develops a process that long, but that's what they end up doing to break the patent. Inside a fluid bed, let's look at one coating column. A single coating column machine, simplest machine there is. You have the area in blue here, this low velocity. The outer zone is the down bed. We call it the down bed because the product is moving down. So there's no real fluidization here. It's a slight, just enough air to keep the product doing this. We don't want it bubbling. We want it just doing this. That's the down bed. When the product gets down here, the area right next to the coating column and the area inside the coating column is a high velocity area. High velocity, low pressure. Products move from high pressure to low pressure. So the particle moves under the coating column. There's a high velocity air here, so it accelerates, it fluidizes, goes past the spray nozzle, gets coated, goes into the chamber where the diameter increases, the product slows down, gently falls back to the down bed, and repeat. And you're going to do that over and over again. So again, down bed, you've got air going through the down bed this direction. But all that air is doing is keeping the product fluffy, so it moves. You have air going through the up bed, but it's higher velocity, the product is being accelerated upward in the up bed. You've got a spray nozzle, the coating partition, and the coating partition gap, the gap between the filter plate and the partition. So we're adding a little bit of hardware here. Again, I love graphics. So here it is in a more graphical form. How you get the up bed and down bed to work, we're going to talk about. But basically, to make the down bed work and the up bed work, you change the ratio of airflow between the two. How we control that, I'm going to show you. And actually, I'm going to step back, just like 4 slides out of order in this presentation. So the first thing we want to look at as far as hardware for Worcester coating is how do you coat multiple coating columns. Wow, that's way back, wasn't it? There we go. Fluid Air designed back in the early 90s an air distribution shutter system. It's easy when you only have one coating column. There's nothing to balance. One spray nozzle, one column. Nothing to balance. Add 2 columns, 3 columns, 5 columns, 7. You must make sure the air inside each zone of the down bed, the air inside each up bed is exactly the same in all areas. Well, how do you do that in an open bowl? Kind of difficult. What Fluid Air developed back in the 90s is a shutter system. So we divide our coating bowl into zones. So in this case, picture 7 zones. 1, 2, 3, etc. So there's 7 individual zones isolated from each other. Now, unfortunately, my pictures go from 7 to 3, but underneath this plate is a series of balancing shutters. So, unfortunately, my picture is a little confusing. Here I show 7, here I show 3.
That's confused me quite a lot of years.
Yeah. I didn't have a good picture. To turn the 7-liter upside down takes 2 people. I can turn the small one upside down myself, so I took the picture myself.
Okay.
So absolutely right. So when we're looking at this, don't be confused. This is 7 coating columns for a 500. This is 3 coating columns for a 300.
Yeah. Okay.
So concept is still the same. On the top side, you have zones. Each zone has a balancing shutter. That balancing shutter is adjusted. Here we go. The balancing shutter is adjusted to ensure that the pressure drop in each zone. Each zone is isolated from the zone next to it. So you balance each zone so that each zone has the same pressure drop. Same pressure drop, same velocity, same amount of air. So we adjust these, and there's a series of gauges on the machine that allows me to adjust the shutters such that they're all balanced. Once they're balanced, I know I have the same amount of air in each zone. So keep that in mind when we start talking about air balancing. So in a multi-tube coating bowl, you have the area outside these columns. It's called what? What's this area called?
Down bed.
Down bed. There we go. I'm going to wake you up yet. The area inside the columns? Up bed. We're still going to use the same bowl. We're still going to use the same chamber. But now we're going to add all this hardware inside our bowl. By using the same bowl, by using the same chamber, we don't offset our evaporation numbers. Most customers learn on drying and then advance to granulation or coating. So when they learn how to dry things, dry is the same here. Same everything. Same lift, same changeovers, same thermodynamics. Here is a 9-tube coating bowl. So you can see here in the bowl, 9 coating tubes. We balance the airflow. There we go, there's a fitting. There's a fitting right there. There's 9 white fittings around the bowl. Those connect to a pressure gauge. That pressure gauge is adjusted so that all the zones, because they're isolated from each other, all the zones have the same pressure drop. Same pressure drop, same velocity, same flow. So what you're trying to do basically, and again I do it, 7 and 3, is to make sure you have 1/3 of the air in each zone, or 1/7 or 1/9, so that each one's the same. You've got to have them the same because 2 reasons. One, that the amount of air is what affects your up bed and down bed. If you have one zone with too much air, it'll actually blow product into the other zones, and you'll bury one of the coating columns. So you have to balance them. They've got to be balanced kind of specific. You want them to plus or minus 1/4 of 1 inch pressure drop. We shoot for a 1/4 inch differential max across the board. Doing so assures that no one column is low. If a column is low, it'll fill with product. Fill a column with product, you keep spraying on it, you'll create one big cluster of product. You don't want that. So you've got to balance the airflows.
So, sir?
Yes?
For adjusting the shutter, we can only do once before it put into use, right?
Right, so what you do during startup, since what we found out is the aerodynamics is different for every machine. Based on the piping, the pipe diameters, the curves, the valve locations. No two machines have the same aerodynamics.
Yeah.
So what we do is on startup, part of my job, or my team's job, hopefully not me, I'm tired of working, is to set up the balancing plate and adjust it. 1,000, 2,000, 3,000, 4,000, 5,000 SCFM. They take it through the entire range and record what the values need to be on the shutters based on the airflow. So now we know what the shutter adjustments are for today's product. We're going to run, it requires 4,000 CFM. We go to our setup table. Setup table says 4,000. Shutter 1 is 60%, shutter 2 is 40%, shutter 3 is 80%. And you set it. So during assembly, you set the shutters. Only once during assembly. Because again, you're not changing, coating doesn't change airflow. Because remember, you're not growing the particle.
If we change product,
you've got a chart. So this product now needs 4,000 CFM. You go to your assembly instructions. Assembly instruction says 4,000. Here's the settings for all 7 columns.
So that means every time when we change product, when we change the airflow rate,
when you change products.
Yeah.
Yes. When you change airflow rate, you don't change airflow rate in the middle of a process.
No.
Because your product's not getting bigger.
No.
Actually,
yes.
yeah, actually I met one project that the coating rate is 200%.
Right.
Yeah.
But your coefficient of lift.
Yeah.
This goes back, remember I told you 1/2 rho v squared SCL. There's no weight in that equation. The coefficient of lift is the shape of the particle. If the shape doesn't change, the lift stays the same. I can use the same airflow to lift it. I've grown 400%. I've done 400% coatings, polymer coatings, yeah. That's my 22-hour run. That one might go from 5,000 to 6,000, but if you look at the table, when you set the table up, you end up with usually the balancing shutter settings. We're going from 37% to 39%. The change is so small that going 1,000 CFM, which is a lot of air, doesn't affect the shutter settings.
Okay.
Now, if you were going from 2,000 SCFM to 6,000, that's a problem.
Okay.
I've never seen that batch inside a balanced airflow to go from 2,000 to 6,000. I've seen 1,000 CFM changes, never had an issue.
Okay.
And that's 400%.
That means we really need to have some kind of table to show.
Well, that's startup. That's what your startup team does.
Yeah, 1,000
Yeah.
open range like this.
Exactly.
2,000 at this, maybe.
And all seven shutters will be different. The reason you use the shutter system, probably should back up a little bit. Think of the air coming through the plenum. Here's your plenum. The air is coming this way. That air is coming in at 200 feet per minute. 200 feet per minute. It's coming in, slamming to the front of the plenum, and wanting to go straight up. So all the air wants to go through the front of the plenum again. Now in drying, we use a turbo flow plate, and it balances it all the way around. I don't care if it's a little more here, a little more there, a little more here during drying. It just creates a big bubble. That's okay. In coating, I can't have all the air here and a little bit of air here. It's got to be exactly the same to within 1/4 of an inch at all columns. So what we do is use the shutters. what normally happens is the front gets closed down, that forces more air to the back, and then you end up balancing the back ones between themselves. But that's something your startup team does, absolutely. Part of our process is to go through and create that table for every project. Because you can't create it ahead of time because the piping layout is different on every machine. I'd love to do it ahead of time, save myself 3-4 days worth of work, but you just can't. Because every piping layout is different. If the air comes down, makes a 90-degree, and then travels 50 feet to the fluid bed, great. If it makes a 90-degree turn 2 feet from the fluid bed, the dynamics inside here are completely different. And you have to change your balancing settings per machine. So you create a balancing table once. Once you have the balancing table, okay, today I'm running product X. That's a 4,000 to 5,000 CFM range. Here's my balancing settings. Tomorrow I'm running Y, and I'm running Y at 1,000 to 2,000. Here's my settings.
Excuse me, sir.
Yeah.
Do you remember I sent you a picture of this picture?
Oh yeah, that's the picture I like.
Is it right?
That's the picture I like. Well, yeah, down here. Here's your balancing shutters.
Yes, shutters.
Well, you're missing a bunch of parts in this picture.
You don't have this.
Right, you're missing a bunch of pictures, a bunch of parts. Yeah.
Yeah, I got it from reading.
Yeah, they're missing. There's a great picture. It's probably a good thing we don't show all the parts because people copy it. There's a great picture on at the trade show that some of you may remember. That was on the TV screen at the trade show.
Oh, yes.
Which shows a breakaway of all the parts, although it's missing. See on the side here, there's a 3-piece. That one goes in between these two, but it's not shown in the picture, which is probably good. If we showed everything in the picture, we'd make it real easy for our competitors to copy it. So if you look at this picture, so here's the air balancing. There's a plate above the air balancing, but between these two is this structure. This structure here is not shown. It should be between these two.
Okay.
This is what separates the 3 zones. It's gasketed, so the air can't run between the zones. It's got to stay. The air can only stay in each zone. There's gaskets. There's separation dividers. All of that's not shown here, and that's how we control the air in each individual zone. That's a nice picture. I like that. We then have the up bed, down bed adjustment plate. Because again, all this does is adjust per zone. Each zone has up bed and down bed. So you then have to adjust up bed and down bed using these shutters. Again, up bed, down bed is a ratio based on the particle size. The bigger the particle, the more air you need on the up bed or down bed ratio. Those are adjusted. There we go. So the up bed, down bed. Traditionally, everyone in the industry adjusts the up bed, down bed by using a drilled plate. Drilled plates on small machines, real easy. Not a big deal. I mean, they're costly, but not that bad. Imagine a machine now that has 9 coating columns. How much it would cost to drill that plate? And remember, every time you drill a hole, you create heat. You run the risk of the plate deforming. The other problem is R&D develops. Thank you. I'm sorry. R&D develops a product today using mini tabs. Tomorrow they want to create a product using granules. That means you got to buy another plate. What if you don't have that plate? You got to wait for it. This is where your competition makes a ton of money. They sell the customer one plate because the customer says we're going to make beads, so they sell them with the machine one plate. R&D is constantly changing what they want to manufacture. So tomorrow R&D wants to do mini tabs or granules or tablets. Every time you change your particle, you're stuck buying another plate. On a small machine, the plates are about, on the Model 2, I think they're $800 a piece. Not so much. Model 2? Yeah. So not so much. Imagine now the plate for this machine if we use drill holes. Imagine how expensive that would be. You're talking, I think when we used to do drilled holes back in the 90s, it was probably a $15,000 part in the 90s. Customers hated that. One, they had every time the R&D wanted to change something, they needed a new plate, they had to wait 4 to 6 weeks, and cut me a PO for $15,000. What we opted to do is go to a series of shutters. Now, before you panic, this is the up bed, this is the down bed. Normally, there is a filter, a mesh screen on top of here. I've taken the mesh screen off so you can see what's happening. Without the mesh screen, particle would fall right through, obviously. What this system does is allow me to adjust 2 plates across each other, changing the ratio of air for the up bed and the down bed. I have 9 separate settings on my plates. So basically, the shutter system, or the up bed, down bed adjustments, are 9 separate plates for the price of 1. Ask your competition when you start bidding against them. Ask the customer, how many plates are you getting? Are you getting a granule plate, a powder plate, a bead plate, a mini tab plate, a tablet plate? Ask them. Because when they ask their customer, their vendor, their competitor, he's going to go, huh? No, you're only getting 1. You want 9? No problem. Let me charge you for it. And again, on a small machine, it's $800. Not a lot. Start getting into the 9-tube machine, and by today's numbers, you're probably $20,000, $30,000 per plate for 9 tubes. So we established this system years ago, is we will use the shutter system to balance the zone. The shutter picture I showed you earlier. We'll then use this series of plates to adjust the up bed and down bed. Again, this is all set during assembly. So you set the zone balancing plates during assembly. R&D or production tells you you're running mini tabs. Mini tabs tell you to set, I wish I had a better picture, right along this edge here, inside this ring, is a series of numbers. 56%, 64%, etc. That shows the ratio of open space, up bed to down bed. So based on the particle size, you set that plate at the right setting, and you're done. Now, go ahead.
I just want to ask Ivan. So I remember Inojet Full Bed air distribution plate also have some special design.
Yeah.
Some plates to assemble with each other.
Yes.
Could you please explain that to Ron?
Okay.
I would like to explain it to you. We don't have a room full of people. You want to confuse people right now? You want to explain to me? So let's.
Just want to discuss.
Yeah, let's do it offline. Absolutely.
Okay.
I don't want to start talking to someone else's machine in a room and have poor Ricky trying to remember, is that Clean Air's design or is that Putin's design? So I definitely want to hear about it. Absolutely.
Okay.
So getting back to the coding the system, we balanced the airflow per zone. We've set the shutters for up bed and down bed. The other adjustability or other hardware is the coding column. Couple unique things to Fluid Air's coding column. First off, we flare the bottom of the coding column. Believe it or not, it's more expensive to create a cylinder and a conical section. Most manufacturers make it nice and simple. They weld a beautiful cylinder, real cheap. With a single tube coating column, it's not a big deal. 9 coating columns, 9 times the cost. If each one adds $500, I just added $5,000 to the machine by having 9. So why would I spend that money? Why would I flare the partition? The reason we flare the partition is to give the particle time to accelerate so that it gets up here in the spray cloud before it's coated. If the cylinder comes straight down, you run the risk of the particle being sprayed right here, where the droplet is a different size. So we allow the particle time to get up here in the spray cloud, which is the optimal place to coat it. That's the other thing our friends at Wheaton, using the Doppler radar and their knowledge on spray nozzles, was able to explain to us, is that where in the droplet cloud do you want to be? Your droplet is different here than right here. And in our earlier processes back in the 90s, we used to see a lot of bearding of our guns because we were trying to coat right here at the tip. By flaring the nozzle, our particle gets all the way up here in the spray cloud where it belongs before we get it wet. The other neat thing about the coating columns, or one of the things that has to be set for production, is the height of the coating column. The height determines how much particles per unit time go past the spray gun. The higher the coating column, the bigger amount of material going past the spray gun, at a fixed spray rate, it means you have less liquid per particle.
Yeah.
Lower the spray coating column, less particles, same droplet or same amount of liquid, your particle now becomes more wet.
Also spray loss.
Well, at the same spray rate, right? It's keeping the spray rate and everything the same.
Yeah.
If I lower the coating column, I get less powder, or less tablets, less product. With the same amount of liquid, I get more liquid per product.
Yeah.
So coating columns are adjustability. Well, not unique, but one of the things Fluid Air did many decades ago is make the coating columns in process adjustable. The main reason we did it years ago is when my first customer with a 7-tube coating column in Canada wanted 400% growth rate. Boy, at the end of the process, he really wanted the coating column higher. The last thing you want to do is stop the process, empty the bowl, raise all 7 coating columns, reload the bowl, restart coating. Again, you're talking an hour and a half worth of work and an operator touching your product. Bad things happen then. So he requested the ability to adjust the coating columns in process. On a small machine, it's pretty simple. We got this device here. You can see actually on this side a little clearer picture. What an operator does is he loosens the lock nuts, turns the jam nut up or down. Here's the ruler, and that raises and lowers the coating column in process while we're running. So it allows him to fix it during assembly, but also allows him to adjust it in process. If I can do it on 1 column, I'd like to do it on 9. So we have the same system built into the 9, only here we have right here a knob, and you twist this knob and that raises and lowers the coating column. In process adjustability, even on a 9-tube system. So we talked about our flared partitions to keep product away from the tips. That works great for coating the particle the same size. A sugar sphere, a mini tab, or tablet, they're all the same size to begin with. What if they're not the same size? What are the different sizes? Well, what do? Fluid Air's got a patented nozzle shield design that basically prevents your large particles have to go up higher into the spray cloud before they are coated. The smaller ones can actually get coated closer, allowing them to grow more rapidly, allowing them all to get to the same size or get to the same particle size distribution range. That's one of Joe's many patents. Joe has more patents than I care to remember. That's one of them. Simple design, works fantastic. There it is right there. So here it is shown on the coating plate. There, the up bed adjustable plate. Here's the partition or the screen, and your spray nozzle would sit inside here. So that's why we're allowed this week. That allows us to coat granules and powders. Is that screen there? If I'm coating beads, sugar spheres, mini tabs, tablets, all the same size, we don't use this. We'll just go with a normal system like this for coating similar size material. This one's designed for dissimilar size materials, powders, granules.
Yeah.
Spray nozzles. I talked about earlier having 3 types of spray nozzles. Coating, Fluid Air has still in our offering 3 coating spray guns. 1 is a standard nozzle, 2 is a self-clearing nozzle, and 3 is an in-process removable nozzle. Tony knows this, Thomas knows this, obviously Frank does as well. I tell every customer during a training session or during a presentation, any vendor who sells you an in-process removable nozzle is doing so because he has not done his job right. If you design the coating system properly, if you've designed your partition, if you've designed your up bed down bed plate your air balancing, and your spray nozzles properly, you should never have to remove a spray nozzle in process. I have not done one, I've not had to remove a nozzle in process late 90s, maybe early 2000. We've stopped selling them. Well, it's still in our book, but I'm going to tell you right now, but any customer who asks for it, I'm going to talk out of it. Sales doesn't like it because that's a big adder. That's a huge adder to a machine, more commission for sales. But any customer or any vendor trying to sell you removable nozzles is doing so because they have not designed the coating fluid bed properly. You don't need to remove a nozzle in process. 2 reasons why you wouldn't want to. 1, fluid beds explode. I don't care if it's aqueous or not. You run the risk of explosion. Every fluid bed adds a risk. When you're removing that nozzle, you unclamp it here. Remember, this is inside the bowl, this is outside. You've now opened the machine to the operator. He's standing right in front of it, holding that nozzle. Usually it's down low, so usually he's like this, opening it. If it explodes right now, what's going to happen to him? He's dead. Or he's in the hospital, one of the two. You don't ever want to open up the machine while it's running. That's crazy talk. So you don't ever want to do it. The second reason is if you're doing it, something's wrong with your design. And I've sprayed polymers, I've sprayed sludges basically, slurries for coatings. Never had a problem with a spray nozzle. Once we changed back in the early 90s to the flared partition, there we go, flared partition, and the air balancing, and the proper shutter systems, I have not needed a removable nozzle. So I will never, you will fight me on every project you try selling one. But we do this, and the reason we keep the slide in here, someone always asks, well, why do you show it then? The reason I show it, I want your customers to understand that when their competition, Glot loves this nozzle, because Glot's design stinks. I want to show your customers why. The reason they use this is because their designs are poor. You should never be removing a part in a process. Come on, that's processing 101.
That's good.
So, really like this. Now, the self-clearing nozzle, the standard nozzle is another one I will never condone selling, because for a few $100s more per nozzle, you get a self-clearing nozzle. The self-clearing nozzle has a shut-off pin that we can retract and extend on command. So when we stop spraying, we extend the pin. That prevents dust or anything from getting into the nozzle. We start spraying, we retract the pin and go to spray. The advantage of that is also if you start getting a plug right at the tip. Should for some reason, the tip's obviously the smallest orifice in the machine. If you've got a dissolved solid and it starts to plug the tip of the spray nozzle itself, you start getting an alarm. When that alarm occurs, what do? The machine automatically takes the pin and goes and break through the blockage. Clear the blockage, keep spraying. Automatically. This is a nozzle you want in your machine. Don't look at the picture because that picture is the wrong picture.
Yeah.
So I say that now. And then look around and see the spray systems, folks. This is not the right picture for the spray nozzle. It just happens to be one that I've had forever in this presentation, and eventually I have to update the presentation. Similar ideas, similar concepts, different glue, different shape and look to it. The other advantage of our spray gun, I use the same spray gun in a model 10, 20, 50, 100, 300, 500, 900, 1,000. Same spray gun. So when you do scale up, you don't change the gun, you change the number of guns. You just spent months developing a process using that spray gun. You know exactly what droplet size you need at what pressure and what flow rate. Why would I now tell you to use this spray gun? But that's what a lot of the competition does. They change the spray gun based on the size of the machine, which means now your poor customer has to go through all that scale up and learn that spray gun. Not to mention they now have 2 spray guns which they can't share parts, so they need double the spare parts. We use the same spray gun. You've learned and developed it for your process. I'm going to add more of them, but your spare parts stay the same, your learning curve stays the same, your spray graph, your spray chart, as far as droplet size relative to spray rate and atomizing air stays the same. I've eliminated one of your variables for scalability. Eliminated it. Wow, I skipped this whole thing. Oh, there's a whole bunch of slides missing in this thing, aren't there? Wow. I'm kind of disappointed in that. What's missing here again, Tony?
Almost like that.
Is that right?
Usually the nozzle is the last page.
Is it? Okay. Some reason, I've got this presentation, obviously I do for groups like this. Tony and I have one we've refined, simplified, and made specific for customers. I'm used to doing that one every day, not this one. The coating applications, a couple changes. We changed filter bags. We mentioned this earlier. If you're doing a coating application, say we're coating a sugar sphere. If that sphere breaks, we do not want it to stay in the fluid bed. Why? Anybody? Your sugar sphere, when it's one piece, has a fixed surface area, the area of a sphere. When you coat that sphere, you now have your sustainable release dissolution profile, because you have a defined area. Crack that sphere in half, the area is now changed. So when you coat it, you potentially shift your product's dissolution. Most customers will use a filter bag on the fluid bed with a larger opening. That larger opening allows the broken parts, broken spheres, broken products to leave the chamber. This way only good, solid material stays in the fluid bed. Where does that product go? We talked earlier, it can go to HEPA filters, but now you plug HEPA filters, you got to exchange them, they're pretty expensive. Usually it's why coating fluid beds we suggest using a dust collector. This way when you break a tablet, it goes upstairs, or I'm sorry, break a sphere, no big deal, it goes to your collection drum on your dust collector, you've not impacted the pressure drop. That's why we suggest dust collectors.
Try it.
Exactly, Torrent. We saw a bunch of them at the trade show, a bunch of different locally made ones. I think they're just about as good, but that's why we use dust collectors. The other significant difference, the liquid delivery system's the same. The liquid delivery system you saw with top spray granulation, the pump, the nozzles, pinch valves, the pressure transducers. I use the exact same liquid delivery system on the exact same machine for granulation or for coating. So again, the customers learned all that hardware. Why give him more hardware? We're going to reuse it. One nozzle, one pump head, every machine. All spinning at the same speed gives me the same liquid flow. All at the same air pressure gives me the same droplet size, every nozzle. So we've maintained the airflow to every nozzle. We've maintained the up-bed, down-bed ratio to every nozzle. We've maintained the liquid delivery rate the same to every nozzle. They're the same nozzles. We've maintained the same atomizing air pressure to every nozzle. And we've maintained the partition height the same to every nozzle. That gives us the same liquid, the same quantity of liquid per particulate, and the same size droplet to each particulate each and every time. And now you spray. Now when you end the coating application, that's the exciting one. I haven't found any way to automate it yet. Most people they know they've got to spray 300 kilos of liquid. At about 250, they'll start taking samples every 10, 20 minutes. And they'll check the samples against the scale. Some of them are actually doing process dissolutions to determine what they're getting as far as releases. Some will just spray the production. They've learned at these settings, you spray 300 kgs and we're done. And they'll do it that way. This is where things get real exciting. Imagine if a drying batch goes wrong, you've wasted what? Half an hour or an hour. Painful, recoverable. Something goes wrong in a coating application. You're 20 hours, say you're 8, you said you had 200%. How many hours for 200% growth?
Sorry?
How many hours did it take you for 200% growth?
I don't know. This is a project from the customer, actually.
Okay.
Yeah.
Okay, so let's just say it's 10 hours. Let's just say you've been running the fluid bed for 10 hours if something goes wrong. You've just thrown away 10 hours of work. This is where everything has got to be very precise, very accurate, very perfect. This is where things get very expensive, which is why high value added products when it comes to coating. But this is where we want to play. I know of a couple of 3-tube coaters out there. I know a couple 4 tubes. Blatt's got a 4-tube. I know of no 5, 7s, and 9s. Not only do I have them, I've sold multiples of them. They run every day. And those I can actually get letter references from most of them for coating. Coating is a lot of hardware to learn. Not only from sales standpoint, but from a customer standpoint, assembly. A lot of, I mean, again, you've got 7 of everything. A lot of parts. The good news is, when they run beautiful. They're boring processes, but they run beautiful. Couple sensors we haven't talked about yet. Well, coating. Let's go back to coating questions. Hang on, I'm ahead of myself. Let's go back to coating questions. Coating hardware. Coating process.
Yeah. By the way, regarding the high coating weight, do we need to change the ball?
No.
The particle grows so
Right.
large.
Right. But again, you got so much free space, it doesn't become an issue. Your customer knows based on his growth where he's going to, so he knows he's got to load X amount of product when he does his batch size calculations. He knows his starting densities or starting volumes and finish volumes.
Yeah.
He knows his bowl volume, so he knows how many kilos he can load to start with, based on the finished volume of the bowl, or finished volume of the product and bowl size.
Okay.
And that's what I wanted to show. That's what I missed, Tanner. Okay, Tony.
You never fulfill your both like coating. You cannot. Let's leave enough space.
Right, that's what you do, is you calculate backwards.
Yeah.
You know your bed's going to grow so much, so you know where to put, and this actually I wanted to see. There we go, that's the slide I wanted. So I keep talking about air balancing. So here's the balanced airflow. If you look inside all 7 tubes, at the end of the process, they're clear columns. If the air is not balanced, what you're going to see is you'll see one of these columns, whichever one is low on the airflow, whichever one's not balanced, the lowest one will be full of material, because the other guys have more air in them. So they're going to overpower the weak one, the lowest one. So here's a product. This one's actually a product in Salt Lake City. At the end of the process, they let me snap a picture in 2010. Whether I told them or not, I can't remember. But you can see at the end of the process, the down bed is full, the up bed is clean. That's what we look for at the end of a process. If you start plugging a column, obviously you'll see plugged nozzles, you see all kinds of issues. But you'll also see it on your air balancing long before it becomes an issue.
Sir?
Yeah.
I have a question.
Oh, here we go.
Yeah.
Here's the underside of a bowl. So this is a 7-tube system. So it's a 500-liter machine. There's one more plate. The air balancing plate we looked at with the shutters, it bolts here. And then you've got the zones all separated by these gaskets, both top and bottom, so that the air can't go from zone to zone, so that all the air has to go through the shutter, fill the zone. Your ratio plate here adjusts the down bed and the up bed. Okay. You also have underneath here, the Marprine tubing here is your liquid line. This is your 1/2-inch atomizing air line. These little 1/4-inch lines, that's your nozzle clearing pin. This is also not, I can't tell. Is that your nozzles? Are our new nozzles?
There are one.
Nope, not our new nozzles. There's someone else's nozzles, yeah.
What happened?
So here's a close-up here. Here's a close-up of the adjustability on a 9-tube bowl. So you crank this pin. Here's the measuring device to let you know what your coating column height is. Oops, wrong nozzle again. I haven't seen. I haven't got a good picture of it yet. Questions on coating. If you're getting better pictures here of coatings.
I have a question about in-process and adjustments. What is the smallest size food that you have?
We can actually do a 5-liter in-process coating partition adjustment. We checked with Joe on this a while back. It might have been Whooshy's machine. We can do a 5-liter bowl in-process coating column adjustability. If somebody really wanted a Model 2 to do it, Joe might do it. It might cost you a few dollars, but Joe might do it on a Model 2.
Joe mentioned he could do.
Right, he can, it's just a matter of doing it, because it takes some effort to redesign everything.
I believe some email Joe mentioned. Maybe next machine we can add this.
Did Artex have the
No. No, Pfizer did.
We quoted.
Right.
They want to add, we quoted, but
Save money.
they don't realize that.
And on a small machine, a 2-liter, 5-liter, even a 10-liter, I'd even go so far as a 20 and a 50. Emptying the bowl's pretty quick. Stop the air, the bowl swings out, you clip it upside down, disassemble it, change the partition height, refill it. Not terrible. The problem is you got an operator's fingers in your bowl in the middle of a process. Oops, I did something wrong. He just ruined the first half of the process. On a bigger machine, think about this, that's only a 7-tube, but the big one, 1,000 liters of product. Do your bulk density calculations, that gives you how many kilos. Imagine emptying that big of a machine just to adjust the column height. So doing it in process, just offering the ability to do it makes it easier. Coatings is where it's at. We got to get a coating machine here in China. If we get one multi-tube machine, a 300, you'll never, no one will buy anything else. Get one customer who's got a product that needs coating at a large scale, you're done. It's a slam dunk.
Quite expensive machine.
Sell a 300. In fact, here, Tony, here's the picture you want to sell. You missed this morning.
300.
Sell that machine. It's a 300.
That's the one. Oh,
That's the same machine.
Same machine. Has a machine.
Same machine. That's the 300 3-tube and a 120 1-tube with the airflow bypass. So you get to show off your bypass capabilities. You get to show off a pilot and a production machine, and you get to show off your multi-tube system. Sell it.
I like this machine.
You and I love this machine.
Yeah.
Thomas and I this morning were talking about it. This thing has so much capability.
Sell it. That's double 11, right?
Okay, Frank, sell 2 of them. Take 2 left. Sell 2 of them.
20% discount.
The exciting thing about all of this training, and I know it's a lot of material in 2 days. It's a lot of material. I gave the presentations yesterday to Lena. Track her down, get a copy of them. Read over them. We're going to schedule another 2 or probably a 3-day class in December to go over this, just review this stuff, go over controls, go over scalability, and of course my friend Polar Drive.
Okay.
Yeah.
So please don't wait to come back here to start looking over material. Look over it now. If you got questions now, shoot me an email. If I can't figure it out, we'll save the question until I can return. But don't wait till I return to look. Oh, gee, I should look over that, huh? Look over it now after the class, Monday morning. Look over it. Think about what was said. Look at the slides. How does it apply to what you're going to be doing? This stuff is pretty straightforward and simple for me, now. But I've been doing it 26 years. Makes it easy for me. Coral loves running processes. Carl likes documentation now. It's quiet, peaceful. Big comparisons, selling points when it comes to coating, multi-tube balancing. Glot has multi-tube balancing, but if you compare the same, a 300 liter machine fluid air to a 300 liter Glot, one less coating column. Usually on average, we've got one more coating column on every machine than Glot. What does that mean? Well, pick the 5 tube for easy numbers. I'm 20% more efficient.
Yeah.
I can coat 20% more product at the same time as a Glot. That means I should pay, the customer should pay 20% more for my machine. Doesn't work that way, but that's how we got to present it. That 9 tube machine's a monster. I'll be very honest with you, I don't like it. Because when something goes wrong at 1,000 liters, the numbers of what goes wrong is 17 million mini tabs. Or 12 million mini tabs. I don't like that number. The 500 liter, the 300 liter machine, I would sell that to my best friend tomorrow. I love those machines. They're workhorses. But that 9 tube one looks great when you tell a customer, yeah, I can do 9. How big do you want to go? Couple of quick sensors we didn't go over. I got a couple 2 minutes here. Couple of sensors we didn't go over. Bag burst and LEL. The bag burst sensor is a device on the outlet of the machine to let us know that we're losing too much product through our filter bag. We could be losing it because the bag is damaged or misinstalled. 2 types of sensors. It can be an analog sensor showing us a percentage, or it can be a digital showing us on or off. I kind of prefer the analog because I can use a warning, a high warning and a high e-stop. LEL sensors, low explosive levels. So that tells us the limits. Shows us the percentage of explosive gas inside the machine or inside the exhaust. We usually use that on customers using solvents. If they're running a solvent, we want to know how much percentage of solvents in the air. Because at a certain percentage, it's no longer safe. So we use an LEL sensor. Filter differential pressure, that's our filter bag pressure drop, or HEPA filter pressure drop, and then our chamber differential pressure drop. That tells us how dirty our filter bag is while we're processing. Bowl ground and bowl in place. Remember, I keep saying for explosion we need fuel, product, we need air, pretty straightforward, we need a spark or heat. Fluid beds love sparks. You've got metal separated by gaskets, which keeps devices at different potential. Different potential creates spark. What we do is actually monitor the bowl ground, the grounding of the system, to ensure everything's at the same potential. If it's not at the same potential, we create an alarm. If you don't fix it, we create an e-stop. That's to protect the machine and your customer. Bowl in place, we actually have a device. Remember, our bowl goes up and down. We have a device to make sure the bowl is fully up, not just touching the gasket, but in the gasket, to ensure that if there's a deflagration, it stays inside the machine. We've seen a couple of Abbott Labs machines in North Chicago that use inflatable seals, where someone doesn't raise the bowl far enough, so it's just touching. No one knows there's a leak until something goes horribly wrong and it blows product out of the leak. So we actually use a bowl in place sensor to ensure the bowl's fully raised. Last but not least is support. Besides having a local team here, which you all are developing, Fluid Air, at least globally, does not charge for phone support. I don't know what Tony's doing here. We do offer 24/7. Fluid Air does offer 24/7 support. Customers got to pay extra for that. We also offer what we call remote services, which gives me the ability to connect to a customer's machine via the internet through a secured firewall, et cetera, I can then look at his status screen. I can look at his PLC. I can look at his computer, allowing me to service it from anywhere in the world.
Yeah.
Now, eventually, the support team here has to learn that. Tony ignores me on that question every time. he doesn't even know what I said right now, do you? You don't know what I said.
不是，我说还有说什么？说什么？说什么？
他这个就是说那个嘛，要你来做这件事
The neat thing for you guys, one of the things I'm going to challenge you people with right now, is I want to know what your customers will pay for an engineer to come to site for one day. Because a Rexroth engineer from Shanghai came to Suzhou to help us work on our pump. He charged me $1,200 US a day. $1,200 US a day was his rate. And that's when Spray Systems called him and asked him to come work for them.
Is that Chinese people or foreigners?
Chinese, Rexroth Shanghai.
Chinese people?
Yes.
You mean $2,400 US per day?
1,200. 1,200.
No.
$1,200
1,200
US dollar.
Well, that's quite expensive.
Yeah, see, that's what I thought too.
I'm pretty sure.
But
that
these are guys with less training, doing less complicated equipment than me, charging the customer $1,200 a day. So I'm gonna challenge you people. Find out what your customers are paying for service, whether for anything. Try to find out, because we've always thought that the China market would pay less, but Rexroth, which is just a hydraulic company, is charging Spray Systems $1,200 US a day. I know that because I got the bill. I want to know what I can charge.
Why did change another supplier?
I will tell you what I charge in the US, anywhere in the world other than China. It's $150 an hour. Once I arrive on your location, and it's $115 an hour for me to travel. So when I leave my house, it's $115 an hour. 10 hours, do the math. Every hour I'm in the building is $150 an hour. And no one else in the world questions it but China. And I agreed with you until I saw the Rexroth bill 2 weeks ago. When I saw the Rexroth bill, I'm starting to wonder if maybe we should charge more.
We should charge more.
Yes.
Absolutely, we should charge more.
That's what I like to hear.
Yes, sir. I actually totally agree with you. We should charge more. Just find a way to charge.
Well, that's what I challenge you. I challenge you guys as you talk amongst your friends.
Yeah, we really
You go to trade shows.